Good day and welcome to part one of our discussion on improper integrals. Up to this point, we've spent significant time evaluating and investigating both indefinite and definite integrals. But the thing I want to note about the definite integrals we've encountered so far is that they have all been over finite intervals. That is, we're going from some number to another number. And a question that you might or might not wonder is, what about a definite integral over an interval of infinite length? That is, maybe an integral from a to infinity of a function, or even something like minus infinity to a number as well. And we will call integrals of this form improper integrals. And the goal of today's discussion is to give a slightly more precise definition of what it means to be an improper integral, and start by evaluating improper integrals that we will refer to as type 1. But before diving in, let's get a little bit of motivation and physical interpretation to go along with these so-called improper integrals. What I would like us to do is evaluate and interpret this area function. So the first thing I'm going to do is just sketch a picture representing the value of that definite integral. If we consider the graph of 1 over 1 plus x squared, very roughly speaking, it's going to look kind of something along those lines. And if we evaluate the integral from 0 to t, where we're here I'm assuming t is a positive value, then a of t would represent this enclosed area, which is why I've called this an area function. In terms of evaluating this integral, I think it's something we should be able to do very quickly and very efficiently. So how about you pause your video, give yourself maybe 90 seconds, and evaluate this integral. So now that you've evaluated, let's kind of compare our notes. An antiderivative of 1 over 1 plus x squared is arctangent. And from the fundamental theorem of calculus, we need to evaluate. So we substitute in x equals t, minus sign, substitute in x equals 0. But note arctangent 0, that is a common value. That's really just 0, so it vanishes. And we're left simply with arctangent of t. And what I would like to do at this point is make a new observation for us. For every value of t, we can calculate this enclosed area, regardless of how large t happens to grow. So a question we could pose might be, what is the limit as t approaches infinity of a of t? Well, from our work above, we know that a of t is arctangent of t, and the limit as t approaches infinity of the arctangent is one of our common limits that we should be familiar with. It's pi over 2. And note what we've calculated. As t goes to infinity, we are finding the area underneath this curve for all positive values of x. So just to put this in a statement, hopefully clearly explaining, we have found that the area under the curve, given by the equation y equals 1 over 1 plus x squared, from x equals 0 to x equals infinity. And just note when we say x equals infinity, we're talking about a limiting sense because infinity is not a number. So this area is pi over 2. Notationally, we might represent this as saying the integral from 0 to infinity, 1 over 1 plus x squared, has the value pi over 2. And the focus of our discussion, at least in the first few videos in this series, is going to be all about improper integrals that have this form. And this is what we refer to as an improper integral of type 1. So let's go ahead and give a somewhat more precise definition and make a few observations about improper integrals of type 1. So if you can evaluate a definite integral from some number a to t for every t bigger than or equal to a, then we can define this improper integral going from a to infinity, and whenever we're dealing with infinities, we need to express this in terms of a limit. So we would write this as the limit as t approaches infinity of the definite integral from a to t of f of x dx. And something we will remind ourselves of repeatedly throughout this section is every time we evaluate an improper integral, our first step is going to be to write it as a limit so that we are able to use, say, the fundamental theorem of calculus to evaluate this integral and take its limit exactly as we kind of indicate it above. Now, note you can similarly define an integral from minus infinity to some number as long as you can integrate from t to b for every t value less than or equal to b. And in that case, we would write this as the limit as t approaches minus infinity of the integral from t to b of f of x dx. And in terms of some language, since we are dealing with limits, we will call the improper integral convergent if this limit exists, and I need to throw in just a little bit more language, and it also has to be finite. So if the limit exists and is a finite number, that is to say it's not plus or minus infinity. And we say the integral is divergent if the limit does not exist or if the limit is plus or minus infinity. And then one other thing you might be wondering is if we can integrate from a to infinity and minus infinity, say to maybe a, what about an integral from minus infinity to infinity? And we can handle an integral from minus infinity to infinity by breaking it up into two of these improper integrals of type 1 that we encountered on the previous page. That is to say, we can write this as minus infinity to a of f of x plus the integral from a to infinity of f of x, where here a, as long as it's the same value in both integrals, can be any number that you choose, but I'm going to be very careful to note that we can only do this if both of these improper integrals converge. So this is true as long as both, and it has to be both of them, of these improper integrals converge. So note, if one of them was to diverge or approach plus or minus infinity, then this original improper integral would diverge as well. So let's finish up our first discussion by just evaluating a very common type of example. So when we get to our next exam or on homework assignments, it's very reasonable to have a list of integrals and we simply say evaluate. We don't need to specify what technique of integration. We also do not need to specify if it's an improper integral or not. Based upon the form, say integrating from 0 to infinity, we can immediately realize or note this is an improper integral. Our first step towards evaluating an improper integral is to rewrite it as a limit. So the limit as t approaches infinity, the integral from 0 to t, x e to the minus x squared. Once we've expressed this as a limit, we're going to focus in on this definite integral. Now, we're also going to use good mathematical notation, so we are going to continue writing this limit at each step until we are ready to evaluate, but our focus is on the integral. So what technique of integration should we apply? And I agree, substitution would work extremely well. If we were to simply let u be minus x squared, du becomes minus 2x dx, and we note that we have an x and a dx, which would be minus 1/2 du. So immediately we can rewrite our integrand so that it only involves the variable u. We have minus 1/2, which is a constant. The constant can be pulled outside of the integral and even in front of the limit, if we would like, to write this as minus 1/2, the limit as t approaches infinity, definite integral with limits of integration yet to be determined, and our integrand is simply e to the u du. But remember, each and every definite integral that we evaluate with a substitution, we must change our limits of integration. So for that lower limit, when x is 0, u is minus 0 squared, which gives us a lower limit of 0. Similarly, for our upper limit, when x is t, u is minus t squared. And now we just proceed on. To evaluate this definite integral, we find an antiderivative, e to the u, and we evaluate accordingly. We replace each u with a minus t squared, minus sign, replace u with a 0. And now that we've evaluated the integral, what remains for us is to evaluate this resulting limit. So just thinking individually about each term. E to the 0 is a constant. It is the number 1. And as t goes to infinity, we need to think about what e to the minus t squared approaches. So maybe a graphical representation would help. So if we have e to the minus x, we think it's an exponential function which is decreasing. Well, similarly, if it's e to the minus t squared, that's also going to be an exponential function decreasing with a t squared versus just say a t. That just means it decreases even quicker. So as we approach infinity, so way out to the right, that function goes to 0. And the value is now minus 1/2, 0 minus 1, which gives us a positive 1/2. So in this case, the language we would use is we would say the improper integral converges. And as usual, a few follow-up observations to finish up. Your work in your notation should look very similar to this. A single vertical column. You're writing equal signs at each step. Your first step is to rewrite this as a limit. You carry that limit through until you evaluate. And when you're evaluating limits, it is perfectly fine to go back to your familiar limit laws and even use something a bit more familiar to us, such as L'Hopital's rule, if it is necessary. We will continue on investigating these improper integrals of type 1 in our next video. So stay tuned. Take care.